All right, kids, so we are going to do some ideal gas stuff, but first, we are no longer going to be able to stay in milliliters if we want to. We are going to have to convert everything to liters, and based on some of the work you've handed in recently, you need a little practice with this. So remember when we have numbers where we put a comma every third digit, and that's because we go to the thousands and the millions and the billions. That's where those threes are. So whenever you're going to jump a decimal, or if you're ever going to have to guess millis or micros or whatever, your best guess is something divisible by 3. And in fact, your best first guess is going to be 3. And I can't tell you how many people would guess 4 places of jumping the decimal. But no, we want to jump 3 places to go from milliliters to liters. Make sure the number is smaller, right? Liters is bigger than milliliters. So it's going to take a lot of milliliters to equal the same amount of liters. And you want to move that decimal 3 places. 1, 2, 3. So 400 mils becomes 0.4 liters, or 25 mils becomes 0.025 liters. Please remember this as we're doing this. You can also use the factor label method or the dimensional analysis we've been doing. Just remember it's 1,000 milliliters for 1 liter. So that now we're going to talk about ideal gases, and this is what my daughter drew about ideal gases, and it's my favorite one, so I'm going to use it. Inspired by her wubble, she has hydrogen, or helium rather, in a balloon, and the balloon is floating away, and you can see here the gases of the wind are there, and the sun is a gas as well. She's done nice work, and I appreciate that picture. And there you have it. So we're talking about ideal gases, and that's my daughter's ideal gas. So the ideal gas law, when we were using the combined gas law, you can solve problems with 3 variables, pressure, volume, and temperature, but you never had to deal with the amount of the gas. That amount did not vary. In fact, we said that P1 V1 over T1 is equal to a constant when the amount is constant. Well, now we want to enter the amount. We want to see what the amount is of a gas. And when we talk amount in science, we talk moles, especially chemistry. And of all the letters that they could have assigned to the value of moles in an equation, they chose N. So scientists have done it again. We will use N as the number of moles. Maybe it stands for a number. That might be it. All right. So the combined gas law, when modified to contain the number of moles, becomes the ideal gas law. And the ideal gas law, which for some reason I still forget to do, the ideal gas law is, I'll do it over here. So it's PV equals NRT. That is hideous. There we go. That's an N. So the pressure times the volume is equal to the moles times R times T. And we call that PIVNERT up and down the hallways of chemistry labs, where R is the ideal gas constant. So pressure, volume, moles is not great. T is temperature, and so R is this ideal gas constant. And thanks to the fact that we can't decide on a pressure unit, we have 3 values for R. 3 values of this bad boy. 3. So, 1R uses atmospheres, and that's 0.0821. 1R uses kilopascals, that's 8.31. And 1R uses millimeters of mercury, and that's 62.4. So depending on what you use for your pressure, that will determine which R you use. But look, everything else, liters, each one has liters, each one has Kelvin, and each one has mole. So what that tells you is temperature always has to still be in Kelvin, and volume always has to be in liters, and moles obviously is going to be in moles. But pressure, since it varies, will be in either atmospheres, and you'll use this R, kilopascals, in which case you use this R, or millimeters of mercury, in which case you use this R. All right, so let's get into some things. Before we get into some questions, let's just really briefly review the math of this. Remember that constants can be limiting. We talked about how if in this Easter egg, I can only fit 48 M&Ms, that means the number of M&M colors times the amount of each color has to equal 48. That constant is limiting. And so here we have 48 green M&Ms, and they all fit nicely in that egg. If I wanted 48 M&Ms of two colors, I have red here and now I have green. Each one, I've decreased the amount of each color, right? In here I had 48 green. Now I have 24 green and 24 red. So there's two colors, but now each one is 24. The point being 24 times 2 equals 48. 48 times 1 equals 48. All right, so if we want to keep increasing the number of colors, we have to keep decreasing the number of M&Ms of that color. So now I have, that would be 16 blue, 16 red, and 16 green, because 16 times 3 equals 48. And if I want 4 colors, now I have 12 yellow, 12 blue, 12 red, and 12 green. So being limited by this 48 M&Ms that fits in this egg means that if I want to increase the amount of colors, I have to decrease the number of M&Ms that have that color. That is a directly proportional relationship. So here we go with 6 colors. 6 colors times 8 M&Ms each. 8 colors times 6 M&Ms each. So the point is, since the M&Ms that can fit is 48, and that constant limits us, as we want to increase the number of colors, which is here in the blue, we have to decrease the number of M&Ms of that color, because they multiply to equal 48. So 1 times 48 is 48, 2 times 24, 3 times 16, 4 times 12, etc. So inverse relationship. So color and amount have what we call an inverse relationship, just like P and V have an inverse relationship. Why is that true? Because PV, when temperature is constant, and we have the gas constant, and we have moles constant, equals a constant. So when P goes up, V goes down. So in order to equal this constant, one goes up, one goes down, just like the M&Ms, colors, and amounts. Likewise, when pressure is constant and R over P is a constant. So volume over temperature equals that constant. If volume goes up to equal this number that's still the same, the T has to go up too. So if this is 2 over 1 and we want to equal 4, then if we raise the V to 4, we have to raise the T to 2 to still equal, I messed that up. But if the constant is 2, so if we say this is 2, then V equals 2, T equals 1. If V equals 4, we have to raise temperature to equal 2 as well. So T goes up to 2. So 4 over 2 equals 2. Anyway, the point is these have a direct relationship and these have a direct relationship when volume is constant. That's just the way it works. Not necessarily something you have to know. So here's our example problem. What is the volume of 1 mole of gas at STP? So let's break down STP. STP means we have a temperature of 273 and a pressure of one of many things, but I like to use 1 atmosphere because multiplying by 1 is easy. So if our pressure is 1 atmosphere and our temperature is 273, we know our moles is 1, so we have 1 mole, and we're looking for our volume. Which of these R's are we going to use? We have pressure units of atmosphere, so we are going to want to use this R here because its pressure units are atmosphere. So plugging into PV equals nRT, and let me do that real quick, PV equals nRT, we have 1 atmosphere times the volume, which we need to find, equals 1 mole times the R, which is 0.0821, times T, which is 273. Wow, that fit. All right, so when you solve for V, V times 1 is V, and then 1 times 0.0821 times 273, that's what that says, believe it or not, and you get 22.4 liters. And that means regardless of the gas, you will have 22.4 liters of volume taken up at STP. And when we did this reaction with a battery and we were dividing water up into its components, you remember that the hydrogen space was twice as big as the oxygen space. And that is because water is H2O. There are 2 moles of hydrogen for every 1 mole of oxygen. And thus, there's twice as much area here, twice as much space by the hydrogen gas as there is in the oxygen gas. So that is that, and that's fun to know. All right, so a child's lungs can hold 2.2 liters. How many grams of air do her lungs hold at the pressure of 762 millimeters of mercury and a body temperature at 37 degrees Celsius? So when we're breaking all this down, we have our volume here, and our volume is in liters, so that's good. We don't have to change that. Our pressure is in millimeters of mercury, and that's fine, but our temperature is in degrees Celsius, and that is not going to do because all of our R's have a K, and as K is the temperature, we got to convert 37 degrees to Kelvin. So our pressure is fine at 762. Our volume is fine at 2.2 liters. Our temperature, though, we have to go to Kelvin. So it's 37 plus 273. And our N, which is moles, is what we're looking for. So of these three R values, which one are we going to use? We're going to want to use this one here because it uses millimeters of mercury. So since that's using millimeters of mercury, we plug all that into PV equals nRT. So we got 762 times the volume, which is 2.2, will equal the N we're trying to find. The R is 62.4, and the T is 310. And there you have it. So you multiply all that out, and you get an N equal to 762 times 2.2. That is 1676. Let's just go with that. And then 62.4 times 310 is 19344. And that's times N. So to isolate this N, we need to divide both sides by 19344. 19344. These cancel. And N, therefore, is equal to 1676 divided by 19344. Now, this is all great work. 0.0867. 0.0866 moles. All right, so that's great. We have moles. But this question is asking for grams. And since it's asking for grams, we now need to use the periodic table, or in this case, it was given to us the molar mass. And we need to multiply the answer of moles, 0.0866, times the grams per mole, which is 29 grams in 1 mole. And I really hate the chicken scratch here, but we're going to have to go with it. So 0.0866 times 29 means 2.51 grams of air is in the baby's lungs. All right. I do apologize for how much a mess that is, but hopefully you're following along pretty good all the same. So finally, the last problem, what is the temperature of a 35-gram sample of carbon dioxide that occupies 550 mils in 0.25 atmospheres? So when we're filling in our PV equals nRT, let's see what we got here. Our pressure is here and it's in atmospheres. That is fine. Our volume is here and it's in milliliters, so we're going to have to convert that to liters. And we have, instead of moles, we have grams. So we're going to do the opposite of what we did before. Pressure is fine as 0.25 atmospheres. Volume, we have to convert milliliters to liters. So we're going to jump this decimal 3 places to 0.550 liters. Temperature is what we're looking for. And the moles is 35 grams divided by, for carbon dioxide, 44 grams per mole. And we got that because CO2 has 1 carbon and 2 oxygen. So carbon is 1 times 12, and oxygen is 2 times 16. So that's 32 and 12, and you add that up, and it's 44. And we got all this from the periodic table. So this comes from the periodic table. So this time, R-wise, we need atmospheres. So we're not going to use that one, and we're not going to use that one. We want to use this R. So PV, so 0.25 times the volume, which is 0.55, will equal the moles, which is, I didn't do the math yet, 35 divided by 44, 0.795. The R we're using is 0.0821. 0.0821, and the T is therefore what we're looking for. So T. Let's put in there. All right, so you do all this math and you get a temperature equal to, I believe it's 2.1 which I wasn't thrilled about, but there you go. Points divided by 0.795 equals divided by 0.0821. And yeah, 2.1. And the units of that are Kelvin. And that's why I wasn't thrilled, because we're basically borderline absolute zero. So that is the unit, or the part of this unit about ideal gas. And there you have it.